Hi, please unmute.
Sorry. Good afternoon, everybody. I apologize for that. Just welcome to this third webinar in the series that's hosted by the Photovoltaics Research Group at Nelson Mandela University. Our speaker this afternoon is Ross Dix-Peek, soon to be Dr. Dix-Peek, and he's going to be talking on the a defect called potentially induced degradation in photovoltaic modules, and associated with that all other aspects in terms of using EL imaging to characterize and look in great detail at cells on a module level. So I'm not going to speak much further. I'm just going to hand over to Ross. Ross, over to you.
Hi there, good afternoon. Today, as Prof said, I am speaking about PV cells and modules with a study of potential induced degradation in photovoltaic modules using an advanced electroluminescence imaging technique to investigate the cells on the module level. I've also included some other defects that are more physically based as well, kind of seeing how much of an effect that they have on the performance of a module. Okay, I suppose we can get to the presentation. Okay, so I'm going to give you a brief introduction to quantitative electroluminescence imaging, kind of where it comes from and how to use electroluminescence in such a fashion. A brief introduction into IV or electrical characterization. You need to know that to make use of the quantitative EL imaging. A brief introduction into potentially induced degradation, the theory thereof, the effect of some physical defects such as cracks or disconnections, how these defects or degradation affects the cells within a module, and then I'll finally get to my results with a potentially induced degradation afflicted module, a module with a cell that has a partial disconnection, that is, two of the bus bars are not properly connected or have electrical contact, and then a module with a cell with a minor set of cracks. Okay, and then I'll summarize and make my acknowledgements. Okay, so electroluminescence is an imaging-based technique and allows us to look spatially across a module. I know Jackie covered a lot of the theory regarding this, so I won't go too much further into that. But it's an international standard for qualitative characterization of a module. And recently there's been development of quantitative methods for electroluminescence imaging, such as power estimation, obviously very useful. And then what I've worked on is individual cell characterization. This allows us to understand what's going on in each individual cell, and then using this you can also estimate module power without the need of a solar simulator. In this presentation I'll look at different defects and their effects on module performance. Okay, as Jackie also mentioned, the cells are typically connected in series. However, some of the more modern designs have parallel strings. However, that's a bit more complicated to characterize using electroluminescence. It is possible. There was a recent paper that did it, but not necessarily as in depth as this. So because they're in series, the module voltage is equal to the sum of the individual cell voltages. Well, there's also a term for series resistance, but for all intents and purposes, this is true. And then because they're in series, the current of the whole module is equal to the current of the individual cells. So looking at the electroluminescence images I show here with a low injection EL image and then a high injection EL image, they both give different sort of qualitative judgments. So if you look at the highlighted box over here, you can see that the cells have different average intensities. Now this could be related to shunting or defect recombination depending, And this is due to the way that shunting or defect recombination will affect the relative cell voltages within a module. And then looking at the high injection EL image with this highlighted section over here, you can see that there is contrast difference across a cell, and that is related to local junction voltage, which can be due to partial disconnection or higher series resistance of the cell in those areas. Okay, so what determines luminescence intensity? I'm going to try to keep this brief because it's more technical than what we need. But in reality, luminescence is dependent on the local material quality and the system, and that's lumped into this C term here. And then it is also related to the local junction voltage and the local thermal voltage. But once you have those values, you can then determine your local junction voltage based upon certain assumptions. It has been shown in previous literature that the calibration factor for a given system and a module for the brightest pixel in each cell has the exact same calibration factor, and therefore it is possible to determine this value and therefore rework it to determine each cell's individual voltage. Now this allows you to extract, at least in the dark, each individual cell's voltage with the current and therefore determine their dark IV curve, and that will allow us, particularly in this case, determine each individual cell's dark IV electrical characteristics, and that can result in determining the whole module's IV curve even in the light when you simulate it. Okay, so the electrical characteristics for a cell are those highlighted over here, where the first section of the equation is for the first diode, because we're assuming a 2-diode model, where we've assumed the ideality factor is equal to 1, and that is for simplification purposes, and it was shown that it was not necessary to have a variable ideality factor. Similarly with the second diode term, excepting it's got an ideality factor of 2. The first diode is typically to take into account bulk recombination, and the second diode factor is meant to take into account defect-related recombination or junction-related recombination, with a third and final term being related to shunt current or shunt resistance. And then for the light, there's just an additional term to take into account the current generated by light. You can use this to adequately describe the current and voltage for a given cell, and it is typically applied to a module as well. However, the voltage is divided by the number of cells, and therefore would reduce the voltage to the correct value for this sort of equation. However, that assumes that you can get a representative cell or an average cell that kind of would work with this. However, as we'll see later on, there is a module that does not exhibit typical IV characteristics, and when you apply this, it wouldn't be able to fit unless you included a variable ideality factor where it came out to being less than 1, which according to physics is not possible, at least for this sort of module. And obviously that doesn't make sense, and we want to be able to make sense of what's going on. It's kind of the point of this sort of characterization. So how do I determine each cell's IV curve or each cell's IV characteristics? When I say the electroluminescence data cube, all it is EL images at different currents being injected into the module. Just a fancy name. And you combine this with that method that I described before to determine each cell's individual voltage, and then you'll have a set of individual IV curves for each cell. Now, when you combine this with the parameter optimization or parameter extraction routine, you can then determine the different IV characteristics, such as your shunt resistance, your series resistance, saturation currents, etc. You can use almost any sort of parameter extraction routine. However, I made use of a genetic algorithm, And that was particularly because it's really good at finding solutions, at least what I've found and I've experienced with this sort of parameter extraction. So then you have a whole set of cell IV parameters. However, the problem with this is that your shunt resistance value is often skewed because, or inaccurate, because of the nature of where in the IV curve the shunt resistance is determined. It's your extremely low current injection. And so what happens is that your EL or your electroluminescence only occurs at typically above 10% of your short circuit current, and there's almost no luminescence beneath that, so you don't have a completely accurate shunt resistance value. That's why I added an additional genetic algorithm or parameter extraction algorithm to determine cell resistance values using those combined IV parameters that I determined before with the dark IV data of the complete module. And this allows for complete cell dark characterization, which you can then use to estimate module power. Thankfully, in the manufacturing process, it's typically done to bin cells based upon their electrical characteristics such as VOC and ISC. That allows us to kind of make a decent assumption to the fact that they should all have the same ISC. It's not perfect. The worst case scenario I've had so far is about 5% error, but considering that that's a complete shot in the dark, aside from the module manufacturer's specifications, and the module was in fact degraded. Okay, so now finally I can get to what is potentially induced degradation. So if we look at this diagram over here, where the left-hand side is the negative side of the PV array and the right-hand side being the positive side of the PV array. Typically what you'd find if you took an electroluminescence image of this entire array is that you'd notice dark cells on the left-hand side or near the negative side of the array, with the furthest left often being the most afflicted with these dark cells or PID. And that would be due to what is actually happening on the module level of where it's coming from. So if we go to the next slide, you'll actually see the construction of a typical module. So what you'll have is the frame with a glass layer, some encapsulant, a cell with an anti-reflective coating and a backsheet. Now on the far left-hand side, where in the previous image, what will happen is that would be the most extreme voltage variation between the cell and the grounded frame of the module. So what would happen is that there'd be an extremely large electric field between the glass and the cell, and that strong electric field will cause the migration of sodium or other positive ions from the glass through the encapsulant, through the anti-reflective coating into the cell, into the emitter, and then it will make its way into the junction. Now this can provide other such problems because it can induce additional energy layers, or energy states within the band gap. I'll discuss in the next slide. However, it must be noted that as you move further from the left towards the positive side, or the negative side to the positive side, that electric field decreases due to the decrease in potential of the cells relative to ground. And that's why you'll note that also that the cells closest to the frame will have a higher likelihood of getting potentially induced degradation. Okay, so as I wanted to speak about, so what happens when the sodium ions move into the material? This is a proposed model by Breitenstein. He has spoken about it with regards to other such defects, not just PID. And so what happens is that when the material gets adequately saturated with these defects, is that will create these extra additional energy levels within the band, which provides a hopping-like mechanism for electrical conductivity. That is an ohmic-like response at these localized points within the cell. Very technical, but along those lines. What happens when it is not so saturated is that you'll have a handful of these energy levels within the band, which will allow for more defect-related recombination. You'll see both of these are the case in the module that I'm going to be presenting on that has PID induced. Okay, so let's go on to some basic physical defects. In the first one, I show you a minor crack or minor damage. This was actually due to thermal stress in this module because it was put in a climate chamber. It was very rapidly had a very rapid change in temperature. You can see there's a minimal area that is affected and should have a negligible effect on the module as a whole, at least in terms of power output. Now with the next one, you can see there is a large area that is affected, and this is from a major crack or could be from a physical disconnection, and this large area is affected and then should have a large effect on the module depending on how much or to what level is it disconnected from the module itself. Then there's busbar disconnection. There was actually a recent paper in PIP with the title Impact on Interconnection Failure on Photovoltaic Module Performance by Colvin et al. And there specifically they speak about disconnection of busbars and the net effect on the module, and then even on the scale of a plant and what sort of losses you can expect. There's other such problems such as localized heating, which can then further degrade the module. So it's not just about the net effect on the IV curve or the power output, but there's also power dissipation due to increased resistance. Okay, so yeah, I'm just giving you a brief kind of simulation on what would happen with different defects or damage to a cell. So in black is the standard cell. You can see it's got a very typical IV curve look to itself, and where maximal power point will occur approximately here. And you can see that relative to the others, it's got a much greater fill factor. So then if you look at the orange one, where I've simulated a halved cell, and in this case what would happen is it's say half the cell is disconnected, and therefore half the current will be produced within that cell when illuminated. Now that would act as a limiting factor in a module, and obviously that has very negative effects such as reverse biasing, etc. Now if you look at the dark blue line, that's a partially disconnected cell. I attempted to simulate what would happen if you disconnected two of the bus bars, for example, two of the bus bars, and that resulted in an increased series resistance, as you can see by the slope over here. Now that would obviously have a decrease in power output, and you can see by the decreased fill factor. So then if you look at the purple line, that is where I've simulated a PID shunted cell, which would obviously decrease power because the decrease in the fill factor. However, if you consider that at maximal power point, let's say assume the rest of the module is this ideal standard cell and it occurs at approximately 7.5 amps, what would happen is that because the module is in series, or the cells are in series, it will be the current will be set at about 7.5 for maximal power point, which would then reduce the voltage of this cell to be at a non-optimal level, being approximately 0.32 instead of, let's say, 0.46. Now, is that effect massive? Probably not, but on the large scale, it would add up. Then similarly with the PID recombination, this is where I just increased the defect-related recombination in the simulation, and what ended up happening is, once again, a drastically decreased fill factor, which would be a loss in power as well. And then if we try to match it at 7.5 amps, you can see very similarly to the shunted cell, there'd be a decrease in the power output of the cell relative even to its maximum power output. Okay, I know that a bit technical, but the net effect is that you lose due to mismatch as well as the decrease performance of the cell. So let's get on to the results. I'll start off with a very special module. This is a module from a previous colleague and student within the group, being Isaac Quembur during his PhD. And even though this module has recovered substantially over time, it is still very interesting and provides a lot of discussion with what is actually going on. And this is what I attempted to answer. So this is the light IV curve of this module before I show you any EL images. Now, as I discussed before, there is a shunt resistance value, and that's typically associated with this side of the IV curve, or the section, and that's one of the linear portions. And then with the series resistance, there's another section over here which is typically associated with series resistance. However, there's an additional tertiary linear section in the curve near the knee. Now that is definitively odd. Now I'm applying my EL technique or method to try to understand what is in fact going on here. Okay, so if you look at the EL images of this module, you can see there is a very interesting pattern with regards to the low injection level or low EL. At 1 amp, you can see that, as I said before, the voltages of the cells are directly related to the average emission from the cell. So you can see that these cells on the left and on the right have a substantial average decrease relative to the rest of the module. Even the upper edge and the lower edge seem to have some sort of decrease in voltage. Now, if you look at the high injection EL image, on the other hand, these cells all appear to be at roughly the same voltage. So there's almost no change, at least in the upper sections of the IV curve, relative to each other for this module. Okay, so now to understand what's going on in some of these cells. So I'm showing you the data directly from the EL imaging data cube that I spoke about, and I'll determine the voltages for 4 different cells. One being C5, which is one of the brighter cells, in the lower EL image, then B2, B1, and A2. Now, if you look at the IV curves themselves, you can see that the C5 follows this trend of standard or an ideal cell, with B2 being slightly lower voltage at both the low injection and high injection than the ideal case being C5, but I wouldn't say it's substantially different. To at least it won't be for any kind of alarm. There's no cause for alarm. However, with B1, the dark blue over here, you can see there's, at the higher injection level, it's absolutely fine, but at the low injection level, there is a substantial decrease in the cell voltage relative to the other 2 cells. Now, that can be associated with defect-related recombination or shunting. Similarly, with A2, there's a drastic decrease in cell voltages, particularly at these low injection levels. Now, that once again could be a sign of low shunt resistance or increased defect recombination, and that would obviously affect the performance of the module. But you can also see something slightly different here relative to the other cells, that even at higher injection levels, the cell is showing lower voltage. Not substantially, at least relative to percentage of the rest of the cell's average cell voltages, but it is at least visible. Okay, so this slide contains both the measured IV data on the left here and the estimated IV data using my technique, and on the right I show the manufacturer specs and the post PID measured values. So as you can see here, when you compare on the right hand side here in the table, the short circuit current showed almost no decrease even with PID induced. And the VOC at this high injection level has limited decrease, but the maximal power point current shows quite a substantial decrease, and that's just due to the electrical characteristics change of the cells. So the maximal power point will obviously shift along this curve, depending on how steep it is, etc., and that would affect the maximal power current. Similarly, the voltage at maximal power point also decreased, but not substantially. But the biggest clear sign that this module is in fact degraded is comparing the manufacturer spec of 295 watts as compared to 278.7 watts. So obviously this module is quite degraded, and that's even at 1000 watts per square meter or 1 sun, which PID doesn't have as much of an effect as the low injection levels. So if we look at the estimated versus measured IV curve, you can see that it well matched the strange tertiary linear portion. And to try to figure out what happened there, I'll discuss in the next set of results. The maximal power point, while it seems to be relatively far off the estimated versus the measured, it must be noted that in this area over here, it is very linear in nature, and so the relative difference between this operational point and this operational point is minimal, at most 1 watt. So it's well within uncertainty. Okay. And then, so to understand what's happening in this module, I'm comparing the electroluminescence images at high and low injection to the shunt resistance values, the saturation current of the defect-related recombination and of the bulk recombination. So what you can see here is that all the cells that are typically associated with the low voltage, or the darker cells within the low injection EL image, can be attributed either to the increase in saturation current of the defect current, defect-related recombination current, or the saturation current of the bulk recombination, i.e. there's an increased probability of recombination of the electron hole pairs. And then if you combine that even further with the shunt resistance values, or the lower end of the shunt resistance values, you would then be able to kind of make sense of this low EL image. Low shunt resistance value implies low EL emission. Similarly, higher saturation current, being the light over here, in both the second diode saturation current and the first diode saturation current, the higher the value, increased likelihood that it's going to be dark in the EL image. Okay, moving on to a partial disconnection module, or module with partial disconnection, particularly being disconnected bus bars or 2 bus bars. And so what you can see in the low injection EL image is that there is in fact a contrast difference between the left-hand side and the right-hand side, i.e. what's connected and disconnected. And similarly, but more exaggerated in the high injection EL image, the left being extremely bright and the right-hand side being extremely dark, at least relative contrast. Now this is due to the fact that the cell's voltage would need to be slightly higher than the rest of the cells, because it is attempting to push higher levels of current through a smaller area, and so the average junction voltage would be higher in this region, while in this dark region it would be lower. That is, it would explain this contrast difference. Okay, now understanding what happens in the performance of the cells. So what I did was I applied my technique and then looked at the relative loss in power, not considering the contact resistance effect of the disconnected bus bars, and then considering those. So the power loss in the middle image is related simply to the mismatch in the electrical characteristics of that module, or of the cells within that module. And once again, this cell within the module is clearly different from the rest. That is, the electrical parameters, at least extracted for the cell, clearly deviate substantially from the rest. And that's largely due to how that less or a lower portion of the cell, or a fraction of the cell, is attempting to put through the same amount of current as the remaining, or as the other cells, which obviously are operating at full surface area. And then when you consider the disconnected bus bars within that cell, it showed a substantial increase in relative lost power. That is, this cell is losing approximately 14% of its possible power production due to electrical characteristic mismatch, as well as the disconnection of that, or in resistive losses. Now that equates to approximately, on the module level, only 0.21% relative power loss. But obviously, if more cells are disconnected within an entire array of modules, there'll be a substantial increase of that power loss. And within that same paper by Colvin et al., they study the impact of this interconnection failure, and that will lead to substantial losses. And if you read that paper, you'll see they'll make a conclusion regarding said loss in power or loss in production. Okay, so in this final result, I'm going to be speaking about a module that was part of my PhD study. I attempted to induce PID within this module using the climate chain that we have and applying a high voltage across the cells to the frame of the module. However, the decrease in power after this exposure, or this attempt at inducing PID, did not substantially decrease the power of the module. It was only approximately 2%, which is within the uncertainty of our solar simulator. So it wasn't degrading, at least in a substantial or significant manner. Okay, so how much of an effect did this slight bit of damage to this cell cause? Now, if you compare the electrical characteristics of the cell pre being in the black circles and post in the red asterisks or stars, you can see there is a minor deviation in the electrical characteristics. Now, could this deviation be due to the induction of some form of defects within the cell? Possibly, but once again, it is so insignificant, I don't think it played any role. And then if we compare the power at 1 sun for this cell, it produced approximately 5.17 watts, post 5.15 watts. So the net effect is only 0.39%. Now, considering that's both damaged and possible PID defects, it is unlikely that either played, or it's unlikely that such a small damage or physical damage to the cell induced any significant problems for the module. Obviously, this damage could degrade further given environmental conditions, but at least in terms of as the damage occurs, there is no substantial decrease in power output from the module, considering that 0.39% would also be relative to the module divided by 60 to get to the percentage loss of the module. Okay, so to summarize it, quantitative EL imaging is effective. You can estimate module power, you can characterize each individual cell, and understand atypical module IV responses, and there's no requirement of a simulator to judge the estimation or to judge the module power. With regards to PID, there's an obvious decrease in module power, and there's different levels and types of defects. There's a possibility of an increased defect-related recombination, and the severity depends on the exposure and the resistance of the module to it. And ohmic-like shunting is also a possible effect. and it is not homogeneous degradation within a module. So part of the power loss of a module will be related to now electrical mismatch between the cells within a module. Okay, then in terms of the physical damage aspect, partial disconnection of bus bars will result in an increase in the parasitic resistance, and the power loss severity is only really related to the number of disconnections, possibly patterns of those disconnections as well. And with regards to minor cell damage or cracks, it is likely only negative effect on power and negligible effect on electrical characteristics. So there won't be an increased likelihood of mismatch within that module. And once again, not to highlight the fact that these minor cracks or damage can possibly in the future cause further degradation when exposed to the elements. So that is an aspect to consider. However, there's no results, at least in this work, to show that. Okay, thank you.
Thank you, Ross, for the very interesting presentation. I want to open the floor to questions. Please type your questions in the Q&A chat section so that we can answer. At present, we don't have any questions. I do have a couple of questions. Well, in fact, I have lots of questions, but just two questions for now. Ross, you know, you did in a way quantify the using the examples that you gave, you know, the power loss and that, but you know, in principle, and this was obviously done on a module level, but on a plant or a string or array level, you know, what sort of impact can you expect if you have multiple defects on multiple cells?
Well, it depends. I suppose, do I have any, if I go back to the sort of, so if we look particularly at this major disconnection, there's, because of the decrease in the photogenerated current, let's say, for example, that could have major ramifications. If the bypass diode doesn't kick in, this cell will take severe heating losses. Obviously, it will be reverse biased. And so either if the reverse bias prevention being the bypass diode works, obviously you'll only lose the string. However, you are at risk of possible fires. I have seen videos of entire, well, not entire strings, possibly 4 modules within a string, in fact, on fire. I don't know if that was related to this, but it is a plausible outcome considering that you would have access, in theory, to, assuming 1000 volts and at even 8 amps, that's 8 kilowatts of power, I think. Yeah, 8 kilowatts of power being able to be dissipated within a single cell would obviously destroy it very quickly. Depending on, you know, that's obviously worst case scenario, but you have the ability to put a lot of energy into a very small area to create quite a hot thing. And there are modules that have cracked due to thermal stresses. You know, there's such a thermal gradient across the glass that I have seen in field the module shattering. But the net effect of other such things, such as PID, would be, if we move forward into this, is that if you have a whole bunch of cells with, because it'll only be half an entire string, you know, that would possibly be affected by PID, is that you'll have a whole bunch of cells operating at substantially worse points on the IV curve to match the current of the entire string. And then you'll have mismatch losses. Now, if you apply that to an entire string on a plant, you know, it might seem like you're only losing 2% power here, 2% power there, but eventually it adds up and adds up depending on the severity of the defect.
Thank you, Ross. I think also you're like touching on the topic that we're going to have next week, where Monfius Kumbuga will be talking on thermal infrared imaging, and observing mismatch and correlating that to power loss as well. Just my other question, while I'm waiting for questions in the Q&A, I'm hoping that colleagues that are present will add to the answers to the questions. Please feel free to add questions. But while we're waiting, I'm going to just something that, as you will be aware, is interesting. Something that's always interested me is getting and clearly this work that you've been doing is showing that we're moving in that direction, but to try and quantify, or to quantify an image, an EL image. So if you look at a module and you say, this module is, you give it a number. Now, I think we're getting there with this type of work, but your thoughts on that?
Well, it becomes more and more difficult when you consider when this is not the case. With these, if we can't fit into these sort of series connected cells, moving towards the possible parallel strings modules, is that it does complicate the matter, but I have some ideas on how to combine the work of our next speaker, or next week's speaker, and basically using thermal imaging combined with electroluminescence image will probably give a better picture of what's going on, because current and voltage heats the module, so there's relation of that to electroluminescence imaging, and perhaps combining that will allow for more accurate, as well as being able to apply that to these new generation modules, which I'm not necessarily a fan of, but it'll allow us to characterize them quantitatively as well, in terms of what is the net power loss due to that. And yeah, so there is obviously that sort of way of thinking to actually provide a number to the net power loss of even these new generation modules. And there's also some work where recently that I've been working on with regards to a mismatch kind of value. It's called EMA, or electroluminescence module mismatch analysis. And it follows a similar train, but working more towards just providing a rating of the module's quality of cell matching. And it's obviously useful as well, because the module itself could be put under strain with cells that aren't adequately matched. And I know we try and match according to ISC and VOC, but there's a whole section of the curve that we're not looking at. Your maximal power point is obviously affected by what the ISC and VOC is, but it's not guaranteed to be an adequate description of that.
Thank you. We have a question. You presented a module that was not affected by PID under standard degradation tests. Can you explain why some modules are not affected by PID?
If we look at the kind of the mechanism in these modules is that I didn't include it in this diagram, but there are extra resistances to take into account. The fact, for example, if there's low sodium glass, for example, it has a lower concentration of sodium or other positive ions, as well as the encapsulant being more resistant to this ion migration. It's also dependent on the anti-reflective coating, and including some cells. In fact, your multicrystalline or polycrystalline is more likely, if not mistaken, to be afflicted, at least with specific types of defects, due to the fact that it's got actual grain boundaries in which the positive ions can more easily migrate through, and causing obviously issues with regards to shunting or increased defect-related recombination. I know that was a big research question, is inducing PID in monocrystalline, and so that's possibly one of the things to look at as well, is comparing polycrystalline to monocrystalline, and so that they have different effects depending on the technology and the different combinations, being the glass, the encapsulant, and the anti-reflective coating.
Right. Thank you, Ross. I don't see any other questions, so I think we're going to call it at that. From my side, thank you very much for the presentation. If Ross can be well, I know Ross is available for communication by email. This webinar will be posted on our webpage, and you'll be able to reach it there, and you can also contact us through the webpage through our research group. So with that, I'd also like to then just make a few acknowledgements. Ross has done so, but I'd just like to reiterate and maybe add. First of all, the PV research group, where a lot of this work was done. Thank you to the team there. Then also, I'd like to acknowledge ESCOM, our partners in this in a project that we are working on, and this webinar forms part of that series, which is part of that project. Then also PV Insight, the module testing company, where a lot of the work was done. And then finally, Chanel Roby from NMU IT Services for helping us through this and making it possible, and of course reminding me to switch my microphone on. Thank you very much, everybody, and goodbye. We'll see you hopefully in a week's time when Monfius Bumbubka will be talking about thermal infrared imaging. Thanks. Bye-bye.